Hello everyone. So we will be reviewing the work and energy in this lecture video. Let's first start with kinetic energy. So kinetic energy is energy that is associated with motion of objects, and in equation is 1/2 mv squared. Now the kinetic energy is a scalar quantity. It depends only on the mass and the speed of the particle. The direction of motion doesn't affect the kinetic energy. And also, as we can see, m cannot be negative. V squared cannot be negative. V can be 0. So kinetic energy can be 0, but it can never be negative. And the SI unit for kinetic energy is joules. Now this is just a illustration that if you have two objects with m moving in two different direction velocity, but they have the same speed. It's just the direction of velocity are the same. They should have the same kinetic energy. Because kinetic energy does not depend on the direction of motion, which means direction of velocity. It only depends on m and speed. Now if you double the mass of the object, keep the velocity the same, you double the kinetic energy. It's 1/2 mv squared. On the other hand, if you keep the mass of the object doesn't change, you double the speed. If you double the speed, because kinetic energy goes like v squared, you double the speed, kinetic energy is going to be increased by 4 times rather than double. So let me write it in equation. This one, kinetic energy is 1/2 mv squared. And for this one is 1/2 m2v squared is 1/2 mv squared times 4. This is kinetic energy. Now we move on to another topic, work. Now work, if you want a non-zero work, we have to have two quantity that is not zero. So in Ricker's vector description, you should have dot product of F and S give you work. Now for us, let's simplify a little bit. So if you have a constant force pointing in one particular direction, and then you have a displacement of the object. Now let's first take F is in the same direction of S. Then by definition, the work done by this force is simply force times displacement. We'll come back to the topic where your F is not exactly in the same direction of S. But from here you can see you have a F. Your F does not necessarily always give you work. You can see if your S is 0. If your S is 0, you always have 0 work, no matter what F you have. So if object doesn't move, the force acting on this object doesn't do any work, because work is force times displacement. If there's no displacement, there is no work. So you have to have force and work at the same time, then you have work. The SI unit of work is joules, the same as kinetic energy. And we can check, actually you can write the 1 joules in Newton times meter. You can also write 1 joules in terms of kilogram meter second square, right? This is 1/2 mv. From 1/2 mv, you can see 1/2 mv square has a unit of kilogram m/s square. And you can check Newton times meter should give you exactly the same unit. They are the same unit. And what does 1 joules means? Basically, if you apply 1 Newton force on a 1 kilogram object, it moves 1 meter. Okay. Let me take it back. Is actually if you apply 1 Newton force on any object, regardless of mass, you apply 1 Newton force on any object, the object moves 1 meter, then the work is 1 joule. Now, as I promised, we need to come back to the case where your force is not in the same direction as the displacement. Now, mathematically, your work should be a dot product of S. Now, if you are going to learn calculus 3, some of you are going to learn calculus 3. So you have two vectors, A and B, and the angle between them is theta. A dot product means you need to find out A in the direction of B. So the component of A in direction of B, which is going to be A cosine theta, right? And it should be A times B. Dot product of A and B should be A cosine theta times B. So it gives you AB cosine theta. Now we apply that. So let's assume the angle between your F and your S is phi. Then the work is the magnitude of F. So this is the magnitude of F. And the same thing, S is magnitude of S. And then phi is the angle between the vector F and the vector S. F is force, S is displacement. So this is how we calculate the work done by a force if the force and the displacement has an angle. Now remember, you always need to find the angle between the force and the displacement for your calculation. It doesn't matter what phi you find. You just need to find this phi between these two vectors and use cosine this angle. It will always give you the right angle, including the sum of the work. Work can be positive, negative, and zero. And from here you can see if your phi is cosine phi is positive, then your work is positive. If your cosine phi is negative, then your work is negative. So what will be the range? So you see, when phi is 0, of course, is positive. Cosine phi is 1. So if phi, and if we draw cosine function, we have 1, and this is 0 when it's 90 degrees. This is 270 degrees. So if your phi is greater than 0 and 90, and phi is greater than 270 to 360. You can also say here is negative 90 to 0. Your work is 0, positive work. And on the other hand, if your phi is from 90 degree to 180 degree, and you will find out your work is negative. So it all depends on the angle between force and S. So it also makes sense, right? So if your force is somewhere here, in these angles, it gives positive work. Now, on the other hand, you have your S and your F is in any of these directions, the work is negative. Okay, now we move on to the work and energy theory. The work done by a net force on a particle will change its kinetic energy, and the work energy theorem tells us the change of kinetic energy, which is final kinetic energy subtract the initial kinetic energy, equals to the total work done on the particle by all forces. Now we will kind of prove work energy theorem in a very special case. The more advanced case we proved in class. So more general case we can prove it in class. Here we prove it. We prove a very special case. You have an object with mass m. So the net force on it is F, and it's constant, doesn't change. Its initial velocity is v1, final velocity is v2. The movement is s. Okay. Now, if we know the net force, right, Newton's second law tells us is going to do constant acceleration motion with acceleration F over m. F over m gives us a, so it's a constant acceleration motion with the acceleration F over m. Okay, constant acceleration motion. We can use kinetic equation to solve it. Now use the fifth kinetic equation that we learned from chapter 2. We should have the fifth kinetic equation. And now I do know my A is F over m. I replace A by F over m times S. And then next step, I multiply 1/2 m on all terms. It's 1/2 mv2 squared, subtract 1/2 mv1 squared equals Fs. Now this is my final kinetic energy. This is my initial kinetic energy equals to work. So we kind of can prove work energy theorem for this very special case, constant force case. And your force doesn't have to be constant, it can change. And the work energy theorem still holds, then we need to use integration to prove that. As we said, we can prove it in class. Okay, so let's do a few examples to help us understand how to calculate the work. Now you have a box which is 10 kilograms. It's dragged by friction. Dragged up 5.5 meter by friction. So this friction actually should be static friction, not kinetic friction. Okay. And the incline has an angle of 36.9 above the horizon. The monitor has a constant speed. And we want to find out what are the work done by those three forces: friction, gravity, and normal force. We need to find out the forces, right? What are the three forces, the magnitude of the forces? Because we need to find the work. Work is force times displacement times cosine phi. Phi is the angle between force and displacement. Now I do know S. So at least I need to find out the magnitude of the force. So you can see this question actually comes back to Newton's either first law or second law problem, Newton's dynamics that we learned in chapter 4. Now, however, which one we need to use now? Now look at the constant speed. Speed is constant, so there is no acceleration for the box. So if there's no acceleration, what's the net force? A equals 0. What is net force? Of course, it equals 0, right? Net force equals 0 if your acceleration is 0. Newton's first law. No acceleration, no net force, or no net force, no acceleration. That's Newton's first law. So we need to use Newton's first law to calculate the three forces. Hope you still remember the first step we need to do is do free body diagram, right? And there are three forces acting on the box. As I said, it should be static friction because there's no motion between the box and the belt. Static friction. And we can build our coordinate system. So net force in x direction is 0. Let's see, net force in x direction, N doesn't have x component, IMG does have x component, and the x component of mg subtract friction is 0. So gives me my friction is x component of mg from trigonometry. So it will be the opposite side of this angle theta. So it should be mg because mg is hypotenuse right now. Mg sine theta. I just need to plug in all the numbers for m and for theta, which is 36.9 degree. I find my friction is 58.8 Newton. Okay. My mg is simple. Mg is 98 Newton. And then I need to calculate what is normal force, right? Normal force. So, which would be in the y direction. Fs doesn't have a y component, so in the y direction, net force add up to 0. So it's n subtract weight in the y direction give me 0. N equals y component of weight, which should be mg cosine theta. Plugging all the numbers is roughly 78.37 Newton. Okay, now I do find those three forces: weight, friction, and normal force. Now I think I'm ready to calculate what are the work done by the three forces. Now put the master equation I need to use here. Work equals F times S cosine phi. Now, I use a phi here so we don't get confused phi and the angle of the inclined theta. Remember, phi is always the angle between the F you want to find out the work and S. Okay, so let's do friction first. Friction is pointing up along the incline. S is also pointing up along the incline. So what is angle phi for F? Fs and S are in the same direction, right? So the angle between them has to be 0 degree. And cosine 0 give me 1. So the work done by friction is just the friction times S times cosine 0 degree. So I need to use the angle between F and S for this angle. So this is just the 1. Plugging all the numbers, I find the work done by friction is 324 joules. Okay. Now I need to find out the angle between S and mg. Now your S is pointing up along the incline. This is 36.9. Your mg is pointing down. This is 90 degrees. So the angle between displacement and the width is 90 degrees plus 36.9 degrees, which is 126.9 degrees. So the work done by width is mg, which is the force, times S, cosine 126.9. equals negative 324 joules. Okay, and then the normal force. This is your S, this is your normal force. This is our normal force. There is an angle between normal force and S, and I know it's 90 degrees, right? So the work done by normal force is normal force times displacement times cosine the angle between normal force and displacement, which is 90 degrees. And I do know cosine 90 degrees is 0. So this work is 0. The work done by normal force is 0, which is not surprising. We have a lot of those kind of example in our class, right? Okay. Now there is one thing I want to point out. So we can find out the net work by all the forces. Normal force 0, weight negative 324 joules, friction 324 joules. Now if you add them all together, it gives you 0 joules. Does it make sense? I think yes, right? From work energy theorem, the net force is 0. The net force is 0 because the box is doing constant speed motion, constant velocity motion. And so the net work is 0. The net work is 0, then the box is doing constant velocity motion, which means its kinetic doesn't change. Kinetic doesn't change also gives you an work energy theorem, so total work done on the object is 0. Okay, now this is for the scenario that the belt lifts the object up. So I want you to think now, if you do have a belt and your object is sliding down, so your S is going to be pointing down along the slide. What will be the work done by gravity, and what will be the work done by friction in this case? And here you are going to have kinetic friction, right? You have weight, and this is your S. Remember, this is not this program. I'm talking about a very similar situation to help you understand. If your S pointing this way, your weight pointing this way, and this angle is smaller than 90 degrees. So in this case, your object goes down, weight is doing positive work. And your kinetic friction would be in the opposite direction of the displacement. The kinetic friction, the angle between kinetic friction and the displacement is going to be 180 degrees. And in this case, your kinetic friction is going to do negative work. So remember, if you want to find out the work, you always need to find the angle between the force and displacement and put it in this cosine phi. It will automatically give you whether the work is positive or negative. Okay, now we do another example using work and energy theorem. So we have a sleigh, 12 kilogram, move straight line, frictionless, horizontal surface. Initial speed 4 meter per second. It moves 2.5 meter. Final speed 6 meter per second. Use work energy theorem. Find the net force second. So work is force times S, right? So we do know S. We don't know work yet, but we can find out work by using work energy theorem. The total work should be change of kinetic energy. This is work energy theorem. And we do know final kinetic energy, initial kinetic energy. So we can find out the work. We can find out the work through work energy theorem. So, and then you can find out what's the force. So let's use the work energy theorem to find out what's the change of kinetic energy first. 1/2 mv2 square subtract 1/2 mv1 square. Plugging all the numbers, we find the work is 120 joules. So now I do know the work is 120 joules. Force times displacement is 120 joules. I do know what is displacement, 2.5. So my force should be work over S, 120 over 2.5 meter gives me 48 Newton. Okay. Hopefully this lecture can help you understand the definition of energy and then the definition of work, and of course how to relate work and the change of kinetic energy through work energy theory. And in the next lecture, we're going to talk about energy conservation. See you next time.